Hello, welcome back. So this is another program that I have written to allow me to point at anywhere on this set, and on the right you'll be able to see like the path that the point is taking in glorious rainbow color. So, this program only runs until it moves out of this circle of 0, 0, radius 2, centered at 0, 0. Because after that point, it really doesn't matter too much what goes on, because it's been mathematically proven that once you move outside of this circle, you just ping off to infinity, and it's only possible over at like -2 to be able to survive at -2. And actually, if I can get like right on it. So what's going on here? What we have is on the right, I believe we have right. On the left, right, we have the angles at which things are happening. So we can see, if I go to exactly 0, 0, if I can get right at 0, 0, which I might, yeah, there. Nothing really interesting happens over there. If we quickly move into the fractal, and I move up to right to 0, 0, this is very difficult. But well, actually, if we do 90 degrees, right? 90 degrees would actually be a very good thing to show off. So, right here, I have chosen a random point on the fractal that is 90 degrees up. So this is a point with 0 real number value and just some arbitrary amount of imaginary, right? There's if you move up and down on this, staying at perfectly 90 degrees, which I didn't do, you would theoretically be able to just, all of those are just imaginary numbers. It just depends on how much, like how big your imaginary number is, basically. But we can see that here at I don't have axes on this one, so I don't know excuse me, the exact number, but at, let's call it 0.25i, we have a 90 degree angle up, and then the next angle is exactly 180 degrees 180 degrees from 0, right? I wish it wasn't tied to my mouse so that I could point. But hey, I'm editing this. Editing Simon. Point to the horizontal line, because I can't. We can see that the next step is a horizontal line going to the left. So that is in degree terms, that is 180 degrees. It's pi radians. And then on the right, we have the excuse me. We have basically the ratio of the previous term and the new term. So for the first term, we go from an angle of 0, right? Just pointing at 0.00, and then moving up to whatever this is. We have an infinite ratio because, you know, I did the new angle over the old angle, right? Just the ratio of the angles. And, you know, an angle of 0 as the old angle will give you an infinite fraction, right? Well, technically it gives you an indeterminate angle, an indeterminate fraction, but for this it's an infinite amount of rate of change. For the next step, we can see that the angle is perfectly twice the first angle, right? This 90 degrees is half of 180 degrees. 180 degrees is twice 90 degrees. And within some computational margin of error, we can actually see that any point on here is exactly until we get to these negatives, until you get to negative i's, every angle here is twice the previous angle. And if we bring up the formula... Hello, this is future editing Simon. I didn't want to try and have to animate all of this text. So, I did the paper recording, but I also realized that I made a mistake when I was initially recording this. So we're going to do this again. You can see me... I figured out that I made the mistake after I already recorded me wasting like 5 pieces of paper trying to write out all of this properly. So, what you can see me doing right now is just writing out the general formula for the Mandelbrot set using polar coordinates of a plus bi, a being the real term, b being the imaginary term, as it is multiplied by I. So, any iteration is the iteration before it squared plus the point that you are working with. We start with the basis that the first iteration, the 0th iteration, is 0. So the first iteration, I'm getting ahead of myself, but the first iteration is simply the complex point that we are looking at, a plus bi, and the second iteration then is the first iteration, a plus bi, the quantity squared, plus a plus bi. So, working through this, we have a squared minus b squared plus 2abi, a plus 2a, abi, yes, check your notes, and then plus the complex point that we are looking at, a plus bi. Now, at this point, we are going to do some polar conversions. So, here I am making sure that I'm doing my polar conversions correctly, checking the internet. So we have the point A, which, if this was a normal Euclidean plane, would be our x value, which is equal to the value of r, the radius, times cosine of theta, the angle from the x-axis that we are working with, and then b would be the y value in a normal Euclidean plane, which is equal to the distance from the origin of the point, and then the sine of the angle. And here I am writing out an explanation for what I have just described. However, I am very bad at writing thetas very small. There's your derivation of where A and B are. And I draw a line. The line's length is r, and the angle from the x-axis is theta, which I wasn't able to draw, so I just made it a point and drew a line. Theta. Now, we can we can go through and look at this formula for the second iteration using these polar coordinates, using the conversions that I have written above the equation that I am now writing. So the first term is a squared, so that is the quantity of r cosine theta squared. The second term, well, it's minus the second term, is b squared, so that is the quantity of r sine theta, the quantity squared. And then, I've noticed an issue, but it's okay, it's not really an issue. So, the next step is 2ABI. Both A and B have an R in them, so we have 2R squared cosine theta sine theta I. It's a technical point, but the I is not is not there on on that equation. And then A plus BI, so plus R cosine plus R sine theta I, also missing the I there. I will continue to miss the I, because I have just now thought of it, and I am not going to waste more pieces of paper doing this again. But now we can group some terms together. You might think it's weird that I am grouping the things in this way. Why don't I just pull the r squared out to both of the terms? You'll see. You can pull the r squared through and still get the same thing, but it gets confusing. So pulling the r squared out of the a squared minus b squared term, we get r squared times cosine squared minus sine squared, plus 2abi, so plus r squared times 2 cosine theta sine theta, and then plus a plus bi. It's just going to be the previous point, right? This is iteration 1, so I wrote it down as iteration 1. Now, here's why I did the silly pairing. It's because the quantity of cosine squared theta minus sine squared theta is actually equal to, it is the double angle form. It is one of the double angle formulas for cosine of 2 theta, and then 2 cosine theta sine theta is the double angle formula for sine 2 theta. So, because we can now do this, we can say that the second iteration is actually equal to r squared times the quantity of cosine 2 theta. Come on, Simon. Plus, there you go, sine 2 theta I. Again, there's supposed to be an I on there. Didn't carry the I through. I might edit an I over this, who knows. Plus the initial point, which is not where... If we included that point, then it would complicate the math. You may have noticed that when I... Here I am just going through the video again before I realize my mistake. So I'm just going to continue talking, and however much of my legs twitching there is, whatever. You may have noticed in the animation for the angle, I'm deriving the angle relative to 0 from the point that the last iteration stopped at. So, hey, editing Simon, otherwise known as Simon, otherwise known as me in 5 minutes. Can we minimize this video and go back to the circles? You can see that we're actually deriving the angle relative to 0 degrees, but up at the point where the last iteration was. Now, in my previous recording that I am now re-recording over, I said something that isn't actually true. Yes, when b is negative, the program doesn't register the double angle, but what's actually happening is the way that my program is deriving the angles, it's not actually looking at it's not calculating the angle from the previous point doing, complex derivation of the angle. What it's actually just doing is finding, the angle of the vector, which means that once you get over 180 degrees, i.e. once your b's become negative, instead of registering 360 degrees, instead of registering anything above 360 degrees, what it's doing is it's just finding, the previous circle angle. So that's why when you're when I'm scrolling down, in the negative i's, the angles are a bit wonky, because after a point, once you go into negative values, the angle that it's bouncing off at is actually, multitudes of rotations around and the angle that it is showing. Which is a thing, but we're not going to have to worry about that. So yes, this concludes me re-recording. Now back to your regularly scheduled programs, probably. Actually, 13 plus 9 what I might actually do is I might cut the video here again, and we go for a third episode, because we're about to start talking about some non-mathematical stuff. We are going to look at the pictures that are happening, not explicitly the mathematics behind any of it anymore. I think I might get a little bit into mathematics again, but not much. So I'm actually going to call the video here, and actually do a proper sign off. Thank you so much for watching. My name has been Simon. You have been amazing. I'll see you next time when we talk about less mathematical stuff and more about the pretty pictures that this makes. Yeah. See you guys next time. Bye.